In this reviewer for electronic circuits, devices, and analysis, let's go over a recap of the introduction to diodes, series diode configuration, parallel diode configuration, effects of temperature on the diode, Shockley's equation, and half-wave and full-wave rectifiers. If you'd like to skip ahead on the video, please check out the descriptions for the timestamps. Let's see what's in this video. So today's video includes the diode concepts, the basic diode diagrams, diode word problems, and rectifier word problems. So specifically, we're going to revisit some of the examples in class, and then we're going to supplement it with some examples from the book. So the examples from the book include the ones with answers and fully detailed explanations at the starting part, and then near the ending part, we're going to try to answer the chapter test from Electronic Devices by Floyd. So topics for further study. So I'm not sure if these topics may appear in the midterms or the prelims, but I think these are relevant. So we have the special purpose diodes, diodes in transformers, diode limiter diagrams, and multimeter readings. So maybe these will be included in a future video once the midterm exam coverage is announced, or maybe you could get a head start of your own and read it from the book. There's also a lot of resources on YouTube if you want to advance study that way. So an important note before we start, we are using the conventional current flow because it is the standard way to show current in electrical engineering. Textbooks may differ on their preferred way of showing the current, but for this video, to keep things simple, we're making it go from positive to negative. As you can see, we're going to match the directions of the diode. So, in the context of this subject, conventional current is also the same representation as the whole current. If you're being asked for the direction of the electrons actually moving, you need to use electron current, which is going the other way. So now let's have a short lesson recap. So this is a recap of chapter 2 of the book. So for section 2.1, let's expand on the direction as shown here. So let's start with the forward bias diode. So it says here that the majority carriers in the N region are the electrons, and they are crossing the voltage barrier. They're overcoming the voltage barrier and also passing through this very thin depletion region. So as seen in this image, the electrons are going from hole to hole and then passing through the diode. So take note, holes are not actually physically there. They are just an easy way that we use to represent the lack of an electron in that region. So as such, if you are using this one, if you are asked to describe what's going on in this image, you can say that the electron current is moving from the N region to the P region. However, if we have this circuit diagram, we can also use the conventional current. So starting with the positive terminal of the battery, we go to the P region. So to remember it, P for positive and N for negative. So the N region connects to the negative terminal of the battery. There can also be other elements in series or in parallel with it, such as a resistor. So if you see R limit, it simply means that this is the resistor that is limiting the voltage that is going through this diode. So again, if we're going in this direction, this is conventional, and this is electron. So the other things here, avalanche occurs in a reverse bias diode if the bias voltage equals or exceeds the breakdown voltage. A diode conducts current when forward biased and blocks current when reverse biased. And the reverse breakdown voltage for a diode is typically greater than 50 volts. So just to add on the next few points, even if this is the direction that we are going, A high enough voltage can cause a high enough voltage, especially from an AC source, can cause the diode to conduct the current in the wrong direction. So that's why we usually typically compute for the voltage. We have to make sure that it is within the normal operating limits. So for section 2.2, this is the VI characteristic curve. So it's called VI because it's the voltage current characteristic curve. The diode current, here the y-axis, is a function of the voltage across the diode, or the x-axis. So the resistance of a forward bias diode is called the dynamic or the AC resistance. So we know from Ohm's law that V is equal to IR. Thus, R is equal to V over I. So while you can't see it in this characteristic curve, you can know that resistance can be found using the slope of this diagram. So reverse current increases rapidly at the reverse breakdown voltage. So there are 5 regions that we'll be expounding on later. But what you need to know is that increases rapidly at the reverse breakdown voltage refers to this area. So that's what I said earlier about a very high voltage being able to force the diode to conduct in the wrong direction. Similarly, when the diode is on and when the diode is on and the voltage is past the barrier potential, it is able to act like a conductor here. For this area in between, the diode is considered off or um, not very conductive. So again, reverse breakdown should be avoided in most diodes. So we prefer to operate in this area rather than over here. This is not the case for Zener diodes since they normally operate on reverse breakdown. So for section 2.3, the ideal model represents a diode as a closed switch in forward bias and an open switch in reverse bias. So basically, this can either be on or off. So if it is forward, it is closed, allowing the current to flow. And if it is reverse biased, it does not allow the current to flow. The practical model represents a diode as a switch in series with the barrier potential. So the barrier potential is similar to a voltage drop. So typically for silicon it's 0.7 and for germanium it is 0.3. So if we have the node voltages, this is V sub A, or the voltage at the anode, and this is V sub K, the voltage at the cathode. So you can expect that here at A it will be higher, and here at K it will be lower. Lastly, for the complete model, it includes the dynamic forward resistance, or R prime D in this case. In practical purposes, sometimes the resistors could be in kilo ohms. Meanwhile, this small resistance could just be as small as 10 ohms, 5 ohms, or etc. So sometimes this is the most used in calculations, especially when it is represented as silicon and germanium diodes, since these ones are not really that common in problem solving. For ideal diodes, we usually use this. So we're going to see an overall formula of what we saw again later. So for now, let's proceed to section 2.4. A DC power supply typically consists of a transformer, a diode rectifier, a filter, and a regulator. So um the scope of our subject at the moment is at this part. we have the output voltage of the transformer or the input voltage to the rectifier. And then when you pass a full wave into a rectifier, it can get either half of the wave or all of the wave. So you should know that rectifiers, half wave rectifiers, are able to get the positive half of it, and full wave rectifiers are able to get the positive and the negative halves of it, except now that they will be all put on the positive side. So a half wave rectifier is usually represented by one diode. So the output frequency of a half wave rectifier equals the input frequency. And the peak inverse voltage is the maximum voltage appearing across the diode in reverse bias. So you should know that the maximum voltage appearing across the diode, its purpose is to make sure that even when the AC voltage source is alternating, it is still able to direct the current in one direction and not to let it go back in the direction that it is meant to prevent. We also have a bit of this for the filtered voltage and the regulated voltage. So this is related to the ripple effect in our lessons near the end of chapter 2.6. So for section 2.5, each diode in a full wave rectifier is forward biased and conducts for 180 degrees of the input cycle. So this is what I was mentioning earlier. There's one diode in a half wave rectifier, so it's only going to have the positive half. For this one, this is a full wave rectifier that is center tapped because these diodes are both tapped into the center. So this is center tapped and it has two diodes. Since this is supposed to capture the positive side and this is supposed to capture the negative side. So when it captures it, the output wave is going to look something like this. So the same output wave can be used to describe this bridge type mechanism. So for the bridge type full wave rectifier, it has four diodes, and usually two of them are on and two of them are off. So as we can see here, there you have an alternating current. So for this branch, it's going to pass through this diode and get blocked for the reverse diode. Similarly, we're going to pass through this diode, and then this one is going to get blocked. So it's going to have the same output as this one. So these are both full wave rectifiers. So for section 2.6, the important concepts here are the ripple voltage. So when we convert an AC to DC with full wave rectifier, so at this part of the process, it's not actually going to be a flat line yet. There's still going to be a little bit of ripple or unwanted AC. So normally, from half wave rectifiers, the ripple is bigger than that compared to the full wave rectifiers. So here are some questions from the chapter test. First of all, to forward bias a diode, to which region must the positive terminal of a voltage source be connected? So it must be connected to the P region. And for number 3, explain how to generate the forward bias portion of the characteristic curve. So the forward bias portion refers to this part where it overcomes the barrier voltage or yeah, that. So to generate the forward bias portion of the characteristic curve, connect a voltage source across the diode for forward bias and place an ammeter in series with the diode and a voltmeter across the diode. So if this is our diode, we place it in series with an ammeter. So that this configuration tells us that current is measured in um yeah in the circuit itself. So whatever current is flowing through the other elements like the resistor is also the same current flowing through the diode. Also, when we attach a voltmeter across the diode, it tells us that there can be different node voltages at different points of the circuit. So for example, we have a diode and a resistor in series. The voltages at these 3 points could be different depending on the other elements like the voltage source and the ground. Specifically, if you'd like to measure the voltage, you have to attach a voltage, or rather a voltmeter across the diode. So slowly increase the voltage from zero and plot the forward voltage versus the current. So slowly increasing the voltage from zero, it is related to the fact that the diode is going to be off when you first run the circuit or power on the batteries. So from there, you have to plot the forward voltage versus the current at this part of the characteristic curve. As past this zero point 0.7 volts for silicon diodes, the diode is going to turn on, and then the current is going to follow the fifth part of the voltage and current characteristic curve. So that's all for the lesson recap. Now we can proceed with the series diode configuration. So everything I said for this item is going to be the basis of what we're doing in this. So for this section, we're going to redo some of the explanations in the book, and then so we're going to redo some of the explanations in the book, and then try to answer something from the chapter tests. So here is a summary of operating regions I explained earlier in the recap. We have 5 operating regions. From left to right, we have reverse breakdown, reverse bias, zero, forward bias below the barrier potential, and the forward bias past the barrier potential. So what you need to know is that past zero point 0.7 for the forward bias, the diode is on. So for forward, 0, and reverse, the diode is off. So it acts as an insulator, or if it is a conductor, it's going to act very weakly. It's going to conduct only a low current. And lastly, when it's past this point, the breakdown voltage, it's going to start conducting current in the opposite direction, which we do not want, since the main purpose of a diode in the first place is to make sure that we are moving current in one direction to prevent the reverse current. Unless, of course, we are using special diodes like the Zener diodes. So Zener diodes usually operate in reverse breakdown. So just some additional information. It was stated earlier that most diodes, especially the common ones, have a reverse breakdown voltage of negative 50 volts. That's why the voltage sources we have in the following problems will probably be less than 50 volts. And everything that goes past that, for example, 1000 volts, it can force the diode to conduct current in the wrong direction and maybe even permanently damage it. So, for example, if we were to, so if you've had a breadboard before, you know that the LEDs or the light emitting diodes can be connected to other elements in the breadboard. So if you use a battery that is too high for the LED and for the other parts like the wires, so this one is going to fizzle out. So that's an example of reverse breakdown. Another is if you put a car battery into a circuit that is not supposed to handle voltages that high, it's going to cause a lot of heating and maybe even a fire risk. So there. Here are the diode approximations. We're going to use the ideal model if it's stated that the diode is ideal. So from the recap, we know that it can be either on or off. It will be on in forward bias and off in reverse bias. So for the practical model, we still have the on for forward and off for reverse bias, except now we have a voltage drop. So for silicon, it's going to be zero point 0.7, and for germanium, it's going to be 0.3. So as you can see from the anode going to the cathode, if we are in forward bias, it's going to drop. So for example, if this is 10 volts, yeah, this is a 10-volt battery. At this node, the anode, we have 10 volts. And here on the other side, we are going to have 9.3 volts. So again, we need to make sure that for the diode to turn on in forward bias, the voltage is able to surpass zero point 0.7 volts. Otherwise, it will just become open, like this one. Or, for example, if it's going in the wrong direction, it's not going to conduct current. So, the complete model is basically just the practical model that also takes into account the dynamic resistance. So, the dynamic resistance is usually negligible and is not included in the computations unless stated in the problem. So sometimes they can be small, like 10 ohms, while the actual values that matter would be in the thousands, like 1000 ohms, 1.5 kilo ohms, 2.5 kilo ohms, etc. So for all of that, they can be summarized by this. So the forward current is equal to the total voltage over the total resistance. So if you are using the complete model, you are going to use this. When using the practical model, you can simply remove the dynamic resistance. If you are using an ideal diode, you can remove the voltage barrier. So this is basically it. This is the formula we're going to be using for the next few items. So here, let's have the most basic example from the book. For the series diode configuration of this figure, determine the voltage across the diode, the voltage across the resistor, and the current across the diode. So here, let's use this formula. We can have E minus zero point 0.7 since it is a silicon diode over the resistance. So this is going to represent the current flowing throughout this loop shown here. So what you need to know is that the current is going to be same across the diode and across the resistor. So using that, we have 8 volts. So let's look at the node voltages. 8 volts going through this forward bias diode. This point is going to be 7.3 volts. And then we're going to go across the resistor. We can notice that this is 0 volts. So this node will also be 0 volts. So going across the resistor, we have 7.3 volts over 2.2 kilo ohms. And this is the current across the resistor. Since it is a series circuit, the current is the same across all the elements. So the current across the diode is also going to be 3.33 milliamps. So what if this diode it will be reversed? So it says here, if the diode is reversed, we find the direction of I is opposite to the arrow in the diode symbol. So according to the models we had earlier, we can now replace the diode with an open switch. So the result is that the network here, where the current across the diode is 0 amps due to the open circuit. It also has a voltage of 0, so that is for the resistor. However, that does not automatically mean that the diode is not conducting any voltage. So remember, the current I is not being conducted across the diode. However, you have to look at the node voltages. So this is going to be 8 volts. This is going to be 0 volts because this is ground. This is going to be 0. And at this point, it's also going to be 0. However, look across the diode. We have the voltage supply of 8 volts or E minus the node voltage on the other side, 0. So that is why the voltage across the diode is still 8 volts. And this one is going to be 0 volts. So that's an important concept that we're going to apply in the exams. So I think that's all that we needed to know since this is all that was discussed in class for series diode configuration. But let's go ahead and answer some examples from the chapter test 2. So here is a modified number 5 and number 7. Originally, we were just asked to identify the direction and the voltage across the diode for an ideal model. So I changed it now that all the diodes are silicon. And then we have to look at the direction. And across the diode and the resistor, we have to find the voltage, the current, and the power. So let's begin. So for this example, determine the following for each component: direction, voltage, current, and power. So first, if there are multiple voltage sources, it's best to start with the node voltages. So here, we know that this is ground, so this is 0 volts. This is 0 volts here and 0 volts here. So looking at this, we know that um, 0 volts on the negative side means that the positive side must be 0 plus 5. And here, similarly, 0 on the negative side and having 8 volts um, as the label means that this part is going to be 8 volts. So recall that current flows from positive to negative, or we could say that it flows from higher to lower. So starting from 8 volts, we go to 5 volts. So since the direction is going in the wrong way, in conventional current, since it is not meeting the direction of the diode, we can say that this is reverse biased. So it's off. So now we can apply the same concepts from the earlier example. There will be no voltage and no current across the resistor. And for this diode, there will be no current across it. However, there will still be a voltage. So looking at the voltage of the anode, so the anode is the flat part of the triangle. We have 5 volts minus the voltage of the cathode, which is the pointy part of the triangle, 8 volts. So we can say that it is negative 3 volts, or that there are 3 volts in reverse bias. So to conclude in our final answer, if we have to write it in word form, we can say that the diode is reverse biased by 3 volts. So it's important to word your answers since the negative signs can have different meanings depending on what convention you're using. So lastly, we have the power. So the power dissipated across the resistor is 0, and the power dissipated across the diode is 0. So for this next example, we can see that we have ground here and ground here. So at first glance, we may assume that if this is 100 volts like earlier, then we might assume that this is 100 and then this part is 0. However, that's not actually the case. Because if you look at the previous example, the voltages are connected directly to the ground. That's why we can make that assumption. But for here, the voltages are not connected directly to the ground. They're connected to nodes. So we can say that the voltage here, the voltage connected to the cathode of the diode is going to be V sub C. And then the voltage across um, this voltage source is going to be V sub C plus 100 volts. So assuming that the diode is on, before we assume that the diode is on, we need to look at the direction of the current. So this is just one line, and we can see that this is most likely to be a positive one. So if this is a positive voltage and this is 0, it's going to flow from that direction going down to here. So for example, um, 99 point something is going to flow down to 0. So that is how we know that the direction is going in this way. So this is forward bias. So knowing that this is forward biased, from 0 volts, we have a voltage drop of 0.7 since it said earlier that all the diodes are made of silicon. So this is negative 0.7 volts at this node, or rather it should be over here. Negative 0.7 volts at this node. And then um, plus 100, we have 99.3 volts. So the node is going to be until here. So now that we know that, we can see that if this is on, therefore, the voltage across the resistor is going to be E minus VD. So it's going to be 100 volts minus 0.7 volts, which is what we showed here. And then from 99.3, it's going to flow in this direction using conventional current to the 0 volts or to the ground. So using that 99.3 volts divided by the resistance, 560 ohms, is going to yield 177.32 milliamperes. So when working with decimals smaller than 0, I tend to not round off until the final answer. So if I'm using a calculator, I'm just going to use store A, store B, etc. But if you do want to round off, you don't round off just here at two decimal places when you're using amperes. For these types of problems, you should move the decimal place first. So 177.32 milliamperes. So similarly, for power, we have P is equal to IV. So we multiply this and this together, and then we get 17.61 watts. So for the parallel diode configuration, we're going to apply the same concepts. So just a short recap. Before we continue, you should know about the voltage splitter and the current splitter. So first we're going to apply the current splitter here. If there is a current that is going to split into different branches, then that means that the current that each branch gets is dependent on the resistances or the voltages that are in that said branch. So let's see. So given this diagram, we are to determine V sub O, I sub 1, I sub D1, and I sub D2 for the parallel diode configuration. So for the applied voltage, the pressure of the source acts as to establish a current through each diode in the same direction as shown in the figure. So right here, we can see that this is the positive side and this is the ground. So we're going to flow across this resistor and split into two branches here and here. So both of these are going to be forward biased. So if these are 10 volts here, then that means at this point it's going to be 9.3 volts since we are having silicon diodes. So that is what this part is. And then we have to um yeah, we have to divide it by the resistance. So we should know that the current is what is flowing through the resistor. So this current of the diode is the same as the current flowing through the resistor. That's why we divide it by 0.33 kilo ohms to get 28.18 milliamperes. So assuming the diodes of similar characteristics, the current here is now 28.18 and it is split across the two diodes. So normally, they are diodes of the same type and characteristics. That will be explained later. But normally, what we have here is that according to the current splitter, it's going to be proportional to their characteristics. But since they're similar, we can just divide by 2. So 28.18 divided by 2 is going to be 14.09. So across each diode, we have 14.09 milliamperes. So here is what I mentioned earlier. What if one diode is silicon and the other is germanium? So remember that when the circuit becomes active for the first time, the diodes will be off. If both diodes are off and they are in parallel, then they must charge first. So they must charge first from 0, 0.1, 0.2, 0.3, and etc. So when that happens, the germanium diode has a lower threshold voltage than silicon. So when this reaches 0.3, it's going to start conducting the current. However, if assuming that they charge at the same time, this one will still be stuck at zero point 0.3 or maybe each reach 0.4, but not 0.7. So this will remain off. And usually what happens in low voltage circuits like 10 volts is that the current will continue to be conducted across the germanium diode and it will be off in the silicon one. So this setup is not usually recommended since it's almost becoming like a series circuit. Like this one is just getting ignored. So keep this example in mind because in the later examples, we're going to check the node voltage without the diode branch because we assume it is off at the start. And if the voltage is high enough to turn the diode on, then we compute the actual node voltage. So for this one, in this parallel diode configuration example, here are our node voltages. So we start at the ground, which is 0 volts, and then across this voltage source, the other one is going to be 20 volts. We also have a silicon diode here, and to determine if it is on or off, let's check the direction of the current. So from plus, we are not going this way, but we're going this way. And then we split into two branches and then go back to the ground. So that's why if this is on and this is silicon, we have a voltage drop of 0.7 and another voltage drop of 0.7 here. So it's useful to draw the node voltages before we get started with the computations. So focusing on the example in the book, we have the current flowing through this R1 is going to be the voltage flowing across it. So from 19.3 minus 0.7, 19.3 minus 18.6, it's going to be 0.7 volts. And then we divide it by its resistance, 3.3 kilo ohms. So the current flowing across resistor 1 is going to be 0.12 milliamperes. Next, we can use Kirchhoff's voltage law or nodal analysis to determine the voltages here. So I'm just going to show that both of them work. So first of all, I'm going to show Kirchhoff's voltage law around the loop, since that's what's here. So we start with 20 volts, and then everything that is encountered is going to be considered a voltage drop. So for silicon, we encounter a voltage drop of 0.7 volts, another voltage drop of 0.7 volts, and then a voltage drop that is unknown. So we represent this as I2. And all of that should equal to 0. So rearranging everything, we can move this to the other side. We have I2 is equal to 20 minus 0.7 minus 0.7. And that's why um, the voltage across this resistor is 18.6 volts. So that's what I was showing here. 18.6 volts minus 0, that's the voltage. And then divided by 5.6 kilo ohms, that is going to lead to the current across R2, which is 3.32 milliamperes. So before we proceed, I just wanted to show you, if you're using this nodal analysis, you can simply skip the loop part. You can simply just use 18.6 minus 0 over 5.6 kilo ohms. So at the bottom node, this one, we can see that the two nodes entering. So in, we have the current across the diode plus the current across resistor 1 going in is equal to I2, or the current across resistor 2, which is going out. So again, we compute for the current across the resistors using I is equal to V over R. But since the diodes do not have a resistance given here or that can be used, we have to use um, yeah, we have to use nodal analysis. So I think this is Kirchhoff's current law, if I'm not mistaken. Correct me if I'm wrong. We have to use these arrows. So it's going to be ID is equal to I2 minus I1. So it's going to be 3.32 milliamperes minus 0.212 milliamperes. So it yields 3.11 milliamperes. So that means the current flowing across the diode is 3.11 milliamperes. So here, let's answer some other examples. So you'll notice I labeled them other. Why other and not parallel? It's because from the word here, parallel diode configuration, you're meant to have two or more diodes arranged in parallel. So as you can see here, there's only one diode here, but there are multiple resistors and multiple voltage sources. So this is probably not going to be included in the exam, but these are just for practice. You can skip ahead to the next section of the video if you want to. Again, you can check the descriptions for the timestamps. But if you want to continue, let's proceed to this one. So first, let's determine the direction of the current flow. So if this is ground, this is going to be 0, this is going to be 0, this is going to be 10, and this is going to be 20, or rather negative 20. Now there is a node that we do not know yet. So we cannot determine if it's going this way or that way. And since there is a diode here, we cannot just assume it is 0 right away. So what do we do in this case? So the reason why negative 0.7 is because if this were on, from 0 volts, we have a voltage drop of 0.7. So that means if we are dropping the voltage, this must be negative 0.7 or beyond that. So again, if you're confused with it, just look at the absolute value of it. It needs to be past 0.7. And the sign will depend on the direction of the diode. But still, if this is on, then that means this one should be less than the value we specified. So first of all, remember our example earlier. It says here that we assume it is off at the start. So if this is off at the start, this is just going to flow in this direction. So now we have the voltage splitter theorem. So now we know that 10 volts is going to indicate the direction is going this way to the negative 20 volts, from higher to lower. So applying the voltage splitter theorem, we know that the voltage is going to be equal to um, the voltage times R1 over R1 plus R2, or simply um, RT or R total. So that's going to be the voltage across one of the resistors. But since they are equal, they're just 10 kilo ohms anyway, we know that it's simply going to get split. So from 10 volts to negative 20 volts, that is 10 minus negative 20, there's going to be 30 volts involved. So that means 15 are going through here. Sorry, we have to make it negative. So 10 volts to 10 volts minus 15 volts is negative 5 volts. And then 5 minus 15 volts is going to equal negative 20 volts. Similarly, if you want a shorter method to do it, you can just get the average. So 10 plus 20, or rather 10 plus negative 20 over 2 is going to be negative 5. So the voltage here at this node is going to be negative 5 volts, assuming that the node is off. The diode is off, I mean. So now that we know that negative 5 volts is less than negative 0.7 volts, we can conclude that this is now on. Okay, so now that we know that this is on, we apply the voltage drop of 0.7 volts across this direction, and we know that this node is now going to be negative 0.7 volts. So now we are able to have the node voltages across each of the components. So now let's compute. So starting with the resistors with both having 10 kilo ohms respectively. So let's see. Um, Take note that the currents will no longer be equal since this is not equal to negative 5 volts anymore. So we can see here across this resistor, the current is going to be 10 minus 10 minus negative 0.7 over 10 kilo ohms. So the current across this one is going to be 1.07 milliamperes. Similarly, for this one, we're going from negative 0.7 to negative 20 volts. So make sure that you're applying the signs correctly. So it must be starting minus end voltage all over the resistance. So the current here is going to be 1.93 milliamperes. So similarly, um, to what we did earlier, this diode does not have a resistance we can use to calculate its current. However, we can calculate using nodal analysis. So we know that I1 going in plus ID going in is equal to the current going out, or I2. So using this, using KCL, we can just rearrange the equation. 1.93 minus 1.07 is going to equal to 0.86. So there are 0.86 milliamperes across the diode in this direction. So now, using V and I, we can compute for the power. So for the second example, under the other examples, let's determine direction first. So starting here, we have 0 and we have 30. We have another 0 here and another 0 here. So there are two nodes we're interested in. First, we need to know what is this node if there is no branch here, or if this is off. And we also have this node. So if the diode is on, we're going to have 0. 0.7 here. If it's off, then this branch will be ignored. So let's see first what we have to say about this node. So marking the node voltages, we now have to look at the voltage of this node without a diode. So if this is open, then this is also not conducting any current. So effectively, we just have a series circuit for now. So let's apply the voltage splitter. So we can see that from this node, 30 volts, we are going down to the ground, which is 0 volts. So that's why the voltage we're going to use as a basis is 30 volts. And across each of the resistors, we need to find the total resistance. So the total resistance is 1.0 plus 1.5 plus 4.7 kilo ohms. And since we are interested in this node, this node, it's easier to compute here since it's directly attached to the ground. So the minus 0 part will make it easier to compute. You could use this one, but it would be a longer one since these two resistors are in series, and you have a long computation for that. So we're going to use this one, 4.7 kilo ohms. So 30 volts times 4.7 kilo ohms over the total resistance in kilo ohms shows us that this resistor is getting 19.58 volts of the 30 volts. So it can be assumed that the remaining 10 point, let's see, 10.42, if I'm not mistaken, should be shared across this resistor and this resistor. So now that we know that this is 19.58, by the way, so 19.58 is very much over 0.7 volts. So again, why 0.7 and why not negative 0.7? It's because here we have the ground here and the voltage drop is going this way. So 0.7 must drop to 0. So this condition is satisfied. So we can now mark this node as 0.7. From here, we can now compute the actual node voltage now that this is on. So what we need to see here is that the current going in is equal to the current going out. So since we do not know the currents yet, we can just use I is equal to V over R. So specifically, for the current across the 1 and 1.5 kilo ohm resistor, we have 30 volts minus the node voltage as the voltage. And then the resistor would be the sum. For this part, the current across the resistor only, we have the node voltage minus 0, or simply Vn, all over 4,700 ohms. And then lastly, for this branch, we have Vn minus zero point 0.7 all over 4,700 ohms. So knowing that, we can now solve for Vn. So using algebra, we simplify both sides of the equation. We cross multiply, we distribute, we transpose, and then we divide both sides by the coefficient. So this is going to be divided by negative 9,700 ohms. It should yield this answer, 14.71649485, or simply 14.72 volts. So now we have finalized this is 14.72 volts. So now that we have figured out the node voltage here, we can compute for all of um, yeah, we can compute for all of the required variables. So here we have the forward bias diode. Its current would be the same as the current flowing across R4, resistor 4. So that is later on revealed to be 2.98 milliamperes. So we can compute it now actually. Have 14.72 minus zero point 0.7, oops, all over 4.7, um, yeah. So that's going to yield 2.98 milliamperes. So for these resistors in series, we should know that at this point, um, the voltages are going to be 30 volts minus 14.72. So my assumption earlier that it should be 10 point something was off. It's because we haven't computed for the node voltage yet. So this is the correct one to use. So 30 volts minus 14.27 is going to be 15.28 volts. And then we divide 15.28 using the voltage splitter for these two. Before that, since these are in series, the current is going to be the same across them. So you can go ahead and calculate that. So 15.28 divided by 2.5 kilo ohms is going to yield this. So the current is going to be the same. And then you can use voltage splitter. So the total voltage is going to be 2.5. So using voltage splitter is 15.28 times 1 over 2.5 for the 1 kilo ohm resistor, and then 1.5 over 2.5 for the 1.5 kilo ohm resistor. So that yields 6.11 volts and 9.17 volts respectively. To double check your answer, when you add these up, they should still equal to 15.28 volts. Next, for this resistor, it's the same as the computation from earlier. And then lastly, for this resistor, we have 14.72 volts over 4.7 kilo ohms. So the current here is going to be 3.13 milliamperes. Last but not least, we have the power. Simply use I and V. So there we go. here are the power dissipated across the resistors and the diode. So if you made it this far into the video, congratulations, because you've just finished the hardest example we have for today. So if you've been able to understand everything so far, the next part should be very easy for you. Since this is just, now there's less of analysis and now there's more of just substitution using equations. So now let's proceed to effects of temperature on the diode. So even if Shockley's equation was discussed first, I think it's better to discuss this one first. Since this is more related to the series and parallel configurations we had earlier. So here's something that you should know. The threshold voltage, just like the voltage splitter earlier, it can be changed. So if the voltage splitter could be changed by the proportions, then the threshold voltage changes according to the change in temperature and the change and sorry, not the change in temperature and the coefficient of resistance. So it's just the same as earlier, original value times something that modifies it. So the threshold voltage is the voltage that must be overcome by the bias voltage. So if this is our characteristic curve, we know that temperature can affect the threshold voltage. It can make it like this. So for example, at room temperature, we know that silicon has a has a threshold voltage of zero point 0.7. So at a certain temperature, it could be um, just zero point 0.5. And again, at another temperature, it could be something like 1. So that is the concept here. Also, we have the temperature coefficient of resistance said to be negative 2.0 times 10 raised to negative 3 per degree Celsius for silicon, and negative 2.5 times 10 raised to the negative 3 per degree Celsius for germanium. So this tells us that temperature affects different materials differently. Lastly, the change in temperature may be expressed in degrees Celsius or Kelvin. So, for example, if we had 25 minus 20 in Celsius, it's still going to be the same as 293. Wait, it's still going to be the same as 298 minus 293 in Kelvin. So, either of these will work. So, it's best to just use Celsius. Next, we have the temperature coefficient on resistance. So, same as earlier, we have the original value times something to modify it will result in the new value. So this time, for resistance, it is also affected by the change in temperature. But instead of the coefficient of resistance, we have the temperature coefficient. So the temperature coefficient, or alpha, is the change in electrical resistance of a substance with respect to change in temperature for specified temperature T sub 1. So again, why did we specify this T sub 1? You should know that the temperature coefficient depends on the temperature. So unlike the temperature coefficient of resistance that has a fixed value according to our textbook, the temperature coefficient must match the initial temperature. So for example, if it says the temperature coefficient at 25 degrees, that means this 25 degrees must be the initial temperature. Otherwise, if it says at 0 degrees, then 0 degrees is our initial temperature. So that is the importance of this alternative formula here. So if it's A sub 0, make sure that you're using R sub 0 and that the change in temperature starts from 0. So lastly, we have the temperature on saturation current. This is the last formula discussed for this section of the video. And instead of um, changing like 1 plus K or 1 plus A times um, change in temperature, we have this instead. So first of all, the saturation current doubles for every 10 degrees Celsius change in temperature. So, for example, if you are at 20, 30, and 40 degrees Celsius, then for every um, 10 degrees Celsius, it's going to double the saturation current. So, what is the saturation current? So, it is the maximum current that flows in a circuit that remains constant despite increases in source voltage. So, this represents the reverse bias leakage current and doubles every 10 degrees Celsius. So, again, if you're asked to explain what this is, reverse bias leakage refers to this part of the VI characteristic curve. So, if the temperature is high enough, eventually the diode will become more prone to failure. So, it could enter the reverse breakdown. And this exponential increase in current that may or may not flow in the wrong direction, um, if it is flowing in the wrong direction, it is called reverse breakdown, or reverse breakdown is the state of it happening, but the name of the effect is called avalanche. So again, these are the three formulas we will be using for the following examples. So these are from some of these are from graded recitation, and others are from the practice exercises in the book. So a coil of aluminum wire has a resistance of 50 ohms when its temperature is 0 degrees Celsius. Determine its resistance at 100 degrees Celsius if the temperature coefficient of resistance of aluminum at 0 degrees Celsius is 0.0038 per degree Celsius. So the first thing you should always look at here is the temperature. So if the coefficient of resistance says it is 0 degrees Celsius, then you must use 0 degrees Celsius as the initial. So these are our given. So we are asked to find the resistance at 100 degrees Celsius. So we are looking for R sub 2. We're going to use the temperature coefficient on resistance formula as shown on the screen. And then we have to substitute the values. So R sub 2 is going to be, it's the thing that we need to solve for. R sub 1 is going to be 50 ohms. Alpha is going to be the coefficient of resistance stated in the problem. And the change in temperature is going to be 100 minus 0. So plugging that in, um, if you're asked to write with proper units, this should have per degree Celsius. So you have to be consistent with your units. So if this is in per degree Celsius, this will cancel out with the Celsius here. The ohms will remain. So when you are writing our final answer, make sure that you have ohms. So simplifying this is going to become 69 ohms. So for number 2, a copper cable has a resistance of 30 ohms at a temperature of 50 degrees Celsius. Determine its resistance at 0 degrees Celsius. Take the temperature coefficient of resistance of copper at 0 degrees Celsius as 0.0043 divided by per Celsius. So at this point, a common mistake that many students use, if the temperature is 50 degrees Celsius and it is the first stated, they automatically assume this is the initial temperature. So not necessarily. This is actually going to be our final temperature or the second temperature, because our coefficient of resistance is specified for 0 degrees Celsius. So identifying the given, we have these values. So we have to determine its resistance at 0 degrees Celsius. Note from the formula that R1 is actually not on the other side. So we are solving for this. If we want to solve for R1, we must divide both sides of the equation by this. So we can rearrange it to be R1 is equal to R2 all over 1 plus alpha times the change in temperature. Like this. So now we plug in the values: 30 ohms, 0.0043 per degree Celsius, and a change of 50 degrees Celsius. So we find that uh, these units will cancel each other, and that the final answer is 24.69 with the unit of ohms. An industrial temperature sensor circuit uses a MOSFET with a threshold voltage of 2.4 volts at 25 degrees Celsius. The equipment is installed near a furnace where the temperature rises to 85 degrees Celsius. If the temperature coefficient of the MOSFET is K is equal to negative 0.002 per degree Celsius, determine the new threshold voltage. So now with the given, let's focus here on 25 degrees Celsius. Now, in a lot of textbooks and even on YouTube, 25 degrees Celsius is specified as room temperature. And you may be familiar with the threshold voltage of 26 millivolts. Now, for the purpose of our examination and per the instructor's instructions, we are not to assume 26 millivolts right away. It is better to compute for the threshold voltage. So the reason why is because of the two textbooks we are using for our course, one of them says room temperature is 26 and one of them assumes room temperature is 27. And when we compute for it, it's not going to be exactly 26 millivolts. It's going to be something like 25.8, 25.9, or etc. So let's show the computation. So here are our given. Um, so the threshold voltage of 2.4 volts at 25 degrees Celsius. And then the temperature rises to 85 degrees Celsius. So there is a change here of 60 degrees Celsius. And then this is our coefficient. So we are to find VTH2. So using the formula for a threshold voltage, we are able to substitute into the equation. So these units will cancel out. And then we are left with volts as the units for the final answer. Inputting this on our calculator, we find that the final answer to two decimal places is 2.11 volts. So next, a rectifier diode in a power supply has a saturation current of 10 nanoamperes at 20 degrees Celsius. The power supply is placed inside a closed cabinet, raising the internal temperature to 60 degrees Celsius. Estimate the new saturation current and describe its effect on leakage current. So it's important to note the prefix here, 10 nanoamperes, can be rewritten as 10 times 10 raised to the power of negative 9. So since the problem states that it raises the internal temperature to 60 degrees, this is our temperature 2, and this is our temperature 1. So now we can identify the given and the formula. So again, the formula we're using is for saturation current. So it's going to double every 10 degrees Celsius change in temperature. So as you can see here, um, this is a change of 40 degrees Celsius. So this is going to double, I think, 4 times. So I'm computing it mentally, 10 times 20, 10 times 2, 20, times 2, 40, times 2, 80, times 2, 160. So let's confirm if that is the case. And yes, it is. So it's going to be 160 nanoamperes. So it's said here that we have an additional question. We have to describe its effect on the leakage current. So since the saturation current represents the minimum leakage, a higher I sub S means more temperature sensitive leakage current that would eventually trigger reverse breakdown via the avalanche effect. So this is what I mentioned earlier. If you see here, the saturation current that represents the minimum leakage is relatively small here at 20 degrees Celsius, which is close to room temperature. However, if you heat up the rectifier diode too much, you can see that the leakage will increase as the saturation current increases. So if this becomes too high, like for example, it reaches 120 degrees Celsius, it could cause permanent damage to um, the rectifier diode. If there is enough reverse current, it could trigger reverse breakdown via the avalanche effect, where it is slowly, very slowly increasing, and then suddenly it increases rapidly. So that is a caveat of this. So it's two raised to something. It's going to be very exponential, and that's why you have to watch out for it. So next, a battery-powered device operates in an outdoor environment. At 15 degrees Celsius, the MOSFET has a threshold voltage of 1.9 volts. During summer, the temperature increases to 55 degrees Celsius. Given K is equal to negative 0.0018 per degree Celsius, find the threshold voltage at the higher temperature and explain how this might affect switching behavior. So, identifying the given as usual, we start at 15 degrees Celsius and end at 55 degrees Celsius. And then we match the other values based on the temperatures. So solving for VTH2, we use this formula and then we substitute 1.9 volts for VTH1, negative 0.0018 per degree Celsius for K, and then a change of 40 volts. So cancel, cancel, cancel. We have the unit and the final answer as volts. And then by computing, we find it is 1.76 volts. So this is just the same as earlier. So now let's focus on the interpretation part. It says, how might this affect switching behavior? So if you're unfamiliar with the term switching behavior, just just think of the word switch. So remember, in the ideal diode, if it is forward biased, it is an on switch. So the current can flow. If it is an open switch or the diode is off, the current will not be able to flow. So let's read the interpretation. A lower threshold voltage means that the characteristic curve will shift to the left, less voltage for the bias voltage to overcome. The MOSFET will require less voltage to create a conductive channel, meaning faster switching. So as you can see here, it started at 1.9 volts, meaning that you need 1.9 volts to turn the diode on. So remember that the diode is actually off first when um, the battery is not yet connected. So it needs time to charge up to 1.9 volts. But here, if the new threshold voltage is 1.76 volts, we know that the bias voltage has a smaller number or smaller voltage that needs to be overcome before it can switch from off to on. So if this is the case, um, if it can overcome the threshold voltage faster, then that means it can switch between on and off faster. So diodes, especially when used in computers, are able to represent data with ones and zeros. So as you can see, depending on the material, it could become faster or slower. So an example here is that when you are playing a game, for example, something that requires a lot of RAM, like Valorant, so the fact that your laptop is heating up may be related to the threshold voltages happening. So it's making sure that the laptop can process the ones and zeros faster. Like this is on, this is off. It's making sure that you have a smooth experience. So we can connect it to the saturation current earlier. If your laptop gets too hot, it could actually cause a lot of reverse current, and that's how it could slow down. So there are a lot of things to consider with temperature. So another one, a solar charge controller uses a diode whose saturation current is zero point 0.5 microamperes at 25 degrees Celsius. On a hot day, the temperature reaches 75 degrees Celsius. Calculate the new saturation current and discuss why high temperature can reduce efficiency. Okay, so for this one, we identified the given. So you should know that micro is equivalent to 10 raised to the negative 6. So at 25 degrees Celsius, this is our initial, and then we rise to 75 degrees Celsius. You have to find the changed saturation current. So using this formula, we're going to check how many times it doubles. So as we can see here, it's going to be 50 degrees Celsius change. So we simply multiply this by 2.5. So multiplying, sorry, not 2.5, 2 raised to 5 times this is going to yield our new saturation current. So if you want to see the full solution, this will cancel. The units will become amperes. And then our final answer is 1.6 times 10 raised to negative 5 amperes, or 16 microamperes. So another way to write this, you could use milliamperes and then just multiply this by 1000. So now let's focus on why high temperature can reduce efficiency. So high temperature causes the higher saturation current to rise from zero point 0.5 to 16 microamperes, meaning that the magnetic core is reaching its maximum capacity to store and transfer energy. So this is akin to the laptop example I gave earlier. The diode is losing its power to store and transfer efficiently, resulting in a voltage drop and acting more like a resistor. So next, we have the temperature coefficient of resistance for carbon at 0 degrees Celsius is negative 0.0048 per degree Celsius. What is the significance of the minus sign? A carbon resistor has a resistance of 500 ohms at 0 degrees Celsius. Determine its resistance at 50 degrees Celsius. So same as earlier, we identified the given. We start at 0 degrees Celsius going to 50 degrees Celsius. And then we multiply it to the coefficient. And then we multiply that to the initial resistance. And we get 488 ohms. Let's focus more on um, the significance of the minus sign. So as we can see here, 500 ohms goes to 488 ohms. So if we can say that the temperature is going down and um, yeah, so if the temperature is going down and the resistance is going down, that means that a negative coefficient can affect whether the resistance goes up or down. So for example, if the temperature goes up and it is still negative, then that means the resistance will go up. Similarly, if this becomes positive, then this will switch. So the resistance is going up in the case that a temperature lowers and the coefficient is positive. And if temperature rises while the coefficient is positive, it's going to become uh, a lower resistance. So to summarize that answer, the negative sign signifies that carbon has negative temperature coefficient, meaning its electrical resistance decreases as temperature increases. So let's check. Its electrical resistance decreases, so 500 to 488, as the temperature increases. So from 0 going to 50. So this interpretation is correct. So that's all for the effects of temperature on the diode. So this is Shockley's equation. It was actually taught before the other effects, but I decided to put it here since it's rather more complicated compared to the other ones. So Shockley's equation is used to find the diode current, which is the current conducted by the diode. So here are the variables that we need to take into consideration. So first is the reverse saturation current, IS. So as we saw from earlier, it's the maximum reverse current that can flow when the diode is reverse biased. The diode voltage is the voltage drop that a diode consumes. So for example, it's zero point 0.7 in silicon and zero point 0.3 in germanium. The thermal voltage is a new concept. Uh, well, rather, it's not that new, but the voltage scale at which the temperature affects semiconductor junction behavior. So this is what I mentioned earlier as 26 millivolts, or rather, approximately 26 millivolts. Later, we can see it's more of 25.8, 25.9, depending on the temperature we have. So the most accurate way is to compute it using KT over Q. So KT over Q is actually the way to compute thermal voltage, where first we start with K. K is the Boltzmann coefficient. So you can find it on your calculator using the constants. So specifically for Casio calculators, it is Casio constant 25. You can find it by using shift 725. So this Boltzmann constant is a proportionality constant between temperature in Kelvin and energy in joules. So it has a value of 1.38 times 10 raised to the negative 23 power if you're using two decimal places. So next, the temperature is expressed in Kelvin. So remember my example earlier about degrees Celsius and Kelvin. So if T sub 2 minus T sub 1 ensures that you can use either Kelvin or Celsius, this one uses only Kelvin because we are scaling from absolute zero. So the absolute zero is the absolute coldest temperature that a material can theoretically have, and that is the basis of our that's the basis of our thermal voltage. We are not basing it from 0 degrees Celsius because there can be things colder than 0 degrees Celsius. For example, it's possible to have negative 10 degrees Celsius. That's why we must use only Kelvin. And lastly, we have the electron charge. So it's the magnitude of a charge of a single proton, which is 1.6 or 1.60 times 10 raised to negative 19 coulombs. On your calculator, it may be accessible by shift 723. So for the purpose of this video, I'm going to use the values only up until two decimal places for now. And then we're going to see what happens if we use a different value. So first, find the PN junction of a germanium diode current for a forward bias of 0.22 volts at room temperature 25 degrees Celsius with reverse saturation current equal to 2 milliamperes. Ah, wait, there's something I forgot. It's the ideality factor. So it may vary per textbook. So according to Wallsted's textbook, it is assumed to be 1. So since this is a textbook we're using for most of the computations, we assume this is always 1 unless stated otherwise. In other sources, germanium is 1 and silicon is 2. So if there is a given, refer to the given in each problem. But if there are none, assume it to be 1 for the purpose of our exam. So here are the given. 0.22 is the voltage across the diode. 25 degrees Celsius is our temperature in Celsius. So we're going to add 273. Saturation current is 0.02 amps and the ideality factor is 1. We are tasked to find we're tasked to find the diode current. So another important note I forgot to mention, I'm going to be using plus 273 for the purpose of um, that is what our instructor specified. So if you are more accustomed to using 273.15 for the conversion of Kelvin, that's also fine. It will just cause a minor um, variation. So using Shockley's equation, when you write it, you have to make sure that this is not multiplied to, but rather raised to this exponent. So before we can substitute it, we don't have the thermal voltage yet. So that's why we have to compute it first with kT over Q. We also have the conversion of Celsius to Kelvin. So the first step in the solution is to compute for the thermal voltage. We put these constants and then we convert, we put the converted 25 degrees Celsius as our temperature. So that should yield 0.02570025 volts. So if you see something like this, make sure that you don't just round off to two decimal places right here because that's going to affect how accurate your answer is. It's better when dealing with very small numbers, don't round it off yet. Just round it off in the final answer. But if you must round off, then it might be recommended to move it first here. So move it by three decimal places. So it is 25.70 MV. So proceeding with Shockley's equation, we're now going to put 0.22 as the diode voltage and 0.02570025 as the thermal voltage. So don't mix those up. It's important to look which is for the diode and which is thermal. So substituting that into the equation, these units will cancel out and we will have amperes as our unit. So the diode across the voltage is 10.43 amperes. So here is another thing. If you rounded it off until here, it's going to have a small difference. It's going to become 10.44 amps. So here is what I meant earlier about the thermal voltage. Room temperature varies per textbook. On YouTube and other places, it's commonly stated that room temperature is 25 degrees Celsius. In Floyd's textbook, it is 26 degrees Celsius, and by Bosted, it is 27 degrees Celsius. So you must either assume the thermal voltage instead, or you must compute for it yourself. So here is another example. A silicon diode has a reverse saturation current of 7.12 nanoamperes at a room temperature of 27 degrees Celsius. Calculate its forward current if it's forward biased with a voltage of 0.7 volts. So again, the ideality factor is not mentioned here. Assume it to be 1. Now, we must find the forward current. So I sub D. Let's use the formulas we used earlier, Shockley's equation and the thermal voltage. So as usual, we start with the thermal voltage. 27 degrees Celsius is equal to 300 Kelvin. So when we put 300 times K over Q, we're going to get this voltage. So 0.025875. So I'm going to store this on my calculator. And I'm going to use exactly what appeared here in my computation. So I sub D is equal to 7.12 times 10 raised to negative 9 over A times E raised to 0.7 volts over 1 times the thermal voltage. So again, make sure that it's raised to, not multiplied. So canceling out these units, we have the final unit to be in amperes. And then we have 3994.93 amperes as the final answer if we computed it this way. So here are some alternative solutions for it. This is why I have so much emphasis on rounding off. When rounding off this to 26 millivolts, the current across the diode is going to be 3507.7104 amperes. So it's a bit far. When using the most precise values that you can, for example, you stored constant 23 into a variable like A, and then you stored constant 25 into a variable like B, and then you use the most accurate conversion for Kelvin, which is including the 0.15, that will add a lot of precision and accuracy to your answer. So most probably the best answer is 4037.29 amperes. Again, this is the best answer in terms of precise values. But if you are instructed to use rounding rules for uniformity in the exams, this may be closer to the actual answer. Just know that it's somewhere near 4,000. So now we proceed to half wave and full wave rectifiers. So as stated earlier, this is where we are right now in the lesson. This is where the concept of the rectifiers will apply. And then later on, for the ripple, this is where we will come into the filtered voltage. So again, the half-wave rectifier has one diode, and it is able to capture the positive parts of the wave. So the negative parts of the sine wave are not captured. Hence, it is called a half-wave rectifier. Full wave rectifier is able to capture both of them, and there are two types of it. There is the center tapped and the bridge mechanism. So to differentiate between them, the center tapped has two forward based diodes that are connected to different parts of this transformer. So one of them is supposed to catch the positive end, and the other one is meant to catch the negative end. But since these are both forward based diodes, by the time that the current is delivered to the load, it's no longer going to be negative, but rather the negative parts are going to become positive. So these work the same way. The difference is that this one, the bridge type mechanism, is more efficient and has less ripple. Also, the way it works is that these ones both go in this way. However, for this one, the reason it's more efficient is when it flows through this way, in addition to working like the center tapped one, it also blocks reverse current based on these diodes. So it should be noted that here the two are always on, and here it's usually two are off and two are on within normal ranges. So anyway, we have these following voltage conversions or factors. So the first thing we need to know is the maximum voltage. So maximum voltage is the peak value of the input AC voltage. So if you can see here, if you have this waveform with 50 volts indicated at the peak, it means that Vm is equal to 50 volts. Now, you should know that we are aiming to turn it into DC, right? So we need a flat line for it. So the flat line represents the average DC output. You should know that um, we divide by pi because um, in a sinusoidal wave, one cycle goes from 0 to pi radians. So for a half wave rectifier, The peak is just here, right? So we only need Vm over pi. But for the full wave rectifier, we need two of these. So we need 2 Vm over pi because in a single cycle from 0 to pi, there are two occurrences of the half wave. So that's why for the half wave we have Vm over pi, and for the full wave we have Vm over pi. So if we were to draw up the DC voltage, the DC of this would be somewhere here, and the DC of this would be somewhere here in the middle. Next up, we have RMS voltage. So RMS voltage is the effective value of the output voltage. It is the stuff that is actually usable. So the root mean square voltage, the easy way to remember it for the full wave rectifier is it has the square root of 2 in the denominator. And for a half wave rectifier, there is no square root. For the efficiency of a half wave rectifier and a full wave rectifier are constants. So represented by the Greek letter nu, 4 over pi squared is the half wave rectifier efficiency, and multiply that by 2 to get the full wave rectifier efficiency. The ripple factor describes the unwanted AC fluctuations. So you can see here that um, when we are trying to convert something into DC, it's not actually perfect, at least not right away. So the ripple factor is going to be something like this. It's basically the fluctuations that are preventing it from becoming a fully DC wave, or rather just a straight line. So this is also a constant for half wave rectifiers and full wave rectifiers, which is 1.21 for half wave and 0.482 for full wave. If you are tasked to show your computation for it, the general formula is gamma is equal to the square root of um, the square of VRMS over VDC minus 1. So again, rectifier efficiency is the ratio of DC output to input power, and ripple factor pertains to unwanted fluctuations. So again, we have the usable part over the direct current squared, and then minus 1, and put that under a square root. That's going to give you the ripple factor. So some additional notes. Full wave rectifiers are generally more efficient. As shown above, they yield a higher DC output voltage, have a higher efficiency, and have a lower ripple factor. Ripple factor demonstrates that AC to DC conversions are not straight lines. Rather, the sine wave has many tiny bumps that resemble a straight line, which is why we get the average DC. So here, we are tasked to find the average value of the full wave rectified voltage. So if it's something like this, it's different than what we usually know. There are no given descriptions in the given. So there's no verbal stuff we can look at. However, looking at here, we know that the highest point of this wave is 15 volts. So that means this is V sub M. So to find the average voltage, the average DC voltage, we just divide it by pi and then multiply by 2. So 2 Vm over pi is equal to 2 times 15 volts over pi, which is equal to 9.55 volts. So another example, find the average value of the full wave rectified voltage in the previous item if its peak is 155 volts instead. So similarly to the previous item, we just change 15 by 15 point, 155 volts, and then we are going to get 98.68 volts. So for this number, an AC voltage with a peak value of 15 volts is applied to a half-wave rectifier with a load resistor of 2 kilo ohms. Calculate the following if the diode is A, ideal, and B, made of silicon. So in our graded recitation, we had only the ideal diode. So I added another part to the question, which is what if it's made of silicon? So let's have the side by side comparisons. This time we're computing for a lot of things: the peak output voltage, the peak output current, the average DC voltage, and the average DC current. So just to draw it, here is what I mean. AC voltage with the peak value of 15 volts is applied to a half-wave rectifier. So the output is going to be something like this. Calculate the following. So first, let's start with the peak output voltage. So we know that the given is the peak is 15 volts and the load resistor is 2 kilo ohms. So that is the same for ideal and silicon diodes. They will differ when it comes to the voltage across the diode. So remember from earlier, if it is ideal, there is no voltage drop. But if it is silicon, there is a voltage drop of 0.7. That is why the peak output voltage, with emphasis on output, like after it has gone out of the diode, is going to account for the voltage drop. So for the ideal diode, we're going to use 15 volts. And for the silicon diode, we're going to use 14.3 volts. Next is the peak output current. So we have V and we have R. So if we have I is equal to V over R, we simply use the peak output voltage divided by the load resistor, or the resistance of the load resistor. So as you can see, for the ideal diode, since there's no voltage drop, the current is going to be higher than in silicon by a little bit. Next, the average DC voltage. So if we have the peak output voltage, like for example, for ideal, it's going to be 15, and for silicon, it's going to be 14.3. We're just going to divide this by pi because remember, we're going from 0 to pi in one cycle of the sinusoidal wave. And also, it's a half-wave rectifier, so we do not multiply by 2. So 15 divided by pi is 4.77, and 14.3 divided by pi is 4.55. Lastly, we compute for the average DC current. So the DC current is just going to be this one, also divided by pi. So for the ideal diode, we have 2.39 milliamps. And for the silicon, we have 2.27 milliamps. So to conclude, what's the difference between the ideal and the silicon diodes? The ideal diode will have no voltage drop or no diode, no voltage across the diode. That will be dropped, and then it will have a higher output voltage. It will have a higher output current. It will have a higher DC voltage and also a higher DC current. Basically, um, the ideal diode is going to have a higher voltage and current compared to silicon because of this voltage drop. So next, a half-wave rectifier has an output with a peak voltage of 20 volts. Find the voltage, efficiency, and the ripple factor. So even if we already know the ripple factor, let's compute for it anyway. And assuming an ideal diode, sketch what the input and output waves would look like. So given the peak of 20 volts, let's sketch the input. So it's going to be 20 volts. So the output could be something like this. where the peak is 20 volts and the baseline is 0. So we are tasked to find VDC, the voltage, efficiency, nu, and the ripple factor. So given this, let's proceed first with the first formula. Or rather, let's show all the formulas here right now. So first of all, the average DC voltage is going to be this divided by pi. So we have 6.37 volts. The average RMS voltage, root mean square, is going to be Vm divided by 2 without the square root, since this is just a half-wave rectifier. So that's going to be 20 divided by 2 is 10 volts. Now the efficiency is going to be a constant. It's going to be 4 over pi squared. So 4 over pi squared is just going to be 0.41. And lastly, the ripple factor. The ripple factor uses VRMS over VDC squared. So you have to get this, and then you have to get this. So 10 squared over 6.37 squared is going to yield this minus 1. So putting all of that under square root, we can see that this is 1.21. So the ripple factor is going to be the same always, assuming that the given are also correct. So, I mean, actually, it doesn't even depend on the given. The ripple factor is always expected to be the same, um, as well as the efficiency. So, to check if your computations are correct, always see if you are able to match these values. It should always fall to 1.21 or 0.482. If it's not equivalent to that, that means something is definitely wrong. So next, a full wave rectifier has a peak output voltage of 30 volts. Find the RMS voltage, efficiency, and the ripple factor. So assuming an ideal diode again, sketch what the input and output waves would look like. So we have 30 volts as the peak voltage. And we also have 30 volts as the peak voltage here. 0 volts as the baseline. And negative 30 volts for the negative side. Okay, so same as earlier, you may notice that we're just looking for the RMS voltage, the efficiency, and the ripple factor. However, if you're computing for the ripple factor, you just need to compute, um, wait, not just, you also need to compute the average DC voltage. So here are our formulas. So this one, since we are having two occurrences of a half wave over 0 to pi, we're going to use 2 Vm over pi. So that's going to be 19.10 volts. The average RMS voltage, since root mean square, we have the square root of 2 in the denominator. So Vm over square root of 2 is going to be 21.21 volts. Lastly, for the efficiency, it's going to be 8 over pi squared because it's a constant. And for the ripple factor, we get the square of this over the square of this. And then whatever that result is, subtract by 1 and then put it inside um, the square root. So that's going to lead to 0.48. So this should, in theory, always be around the same answers, like the ones shown on the formula page. So in addition to this, we know that the average DC voltage is around somewhere here. It's 19 point, yeah, 19.10. And also for this one, for the half wave rectifier, you can see that it is 6.37. So it's going to be relatively low when compared to um when compared to the peak voltage. So I think that's all for today. Well, that's most of the topics that were discussed. But if you are still looking for topics for further study, since it's mentioned that the last two items were not from our discussions but from the module, you may be interested in studying special purpose diodes like the Zener diode, diodes in transformers, like what happens if there's a turn ratio, and then when there's a turn ratio between these two coils, you can still apply the series and the parallel concepts discussed earlier. We also have the diode limiter diagrams. So I think these are similar to clampers, if I'm not mistaken. And also, applying the voltage here, you can also apply what I taught you about the series and parallel to find what is going to be the voltage output here. Lastly, for multimeter readings, while technically not taught, it should be implied since you can just look at the nodes, the nodal voltages, and then analyze what you're supposed to find from there. So I think that's all for today. Thank you so much for watching and good luck for your exams. Thank you so much and have a nice day. This is KJ signing off.